Hi, everyone. It's David Pompiani again. So, ice cores are a crucial link for us to understand past climates here on Earth. However, there's a problem with most ice cores. They're really, really short. And so finding the longest and oldest ice is a big priority among scientists. Most of this old ice happens to be hidden in Antarctica. So finding some of this old ice could solve some of the mysteries we're looking in the past, such as this mid-Pleistocene transition when the pace of climate change on Earth changed. In a groundbreaking new study in 2022, nuclide dating from the Valley in Antarctica revealed some of the oldest ice on Earth. And the lead author, Marie Bergelin, is here on the podcast to talk about the results they found in her paper. So, Marie, welcome to the podcast.
Thank you.
Thank you for being here. Dr. Marie Bergelin is a postdoctoral researcher at the Berkeley Geochronology Center. And like I just said, she has published in the Cryosphere this fascinating paper that presents results showing that there could be ice up to 4 to 5 million years old preserved in Antarctica, way older than we used to think ice could last on Earth just through losses and sublimation. So I want to begin, Marie. You've been to Valley. You went down there and actually were present when the core was recovered, right?
Yes.
So Valley is unique because it is a very dry, cold valley. So can you explain why that old ice happens to be found in that valley? And how did you and your colleagues determine that would be the place to look?
So this is part of my PhD project. So finding the ice and going down there kind of goes a little bit further back in time where I was not present. But my advisor, Jakob Pukkonen, happens to have flown over Oak Valley, going to another valley for surface processing dating. And he happened to look down into Oak Valley and see this sort of bulk shape in the middle of the valley. And he was just like, interesting. Normally, the middle of a valley wouldn't bulk up. It would be like more of a bowl shape, right? So that kind of puzzled him. And he did a project prior to the ice core project that we did, where he went down and they sampled the surface and they dug into the surface and discovered that it actually had buried ice underneath that bulging shape in the middle of the valley. And it did surface exposure dating, so figuring out how long the rocks have been at the surface, and found it to be more than about 1 million years. So indicating that the ice underneath it is most likely older than that. So the current project that was my PhD and I was involved with, a part of, was to go back to Oak Valley, dig down into the ice, and then actually take ice cores back home to see if we can figure out the exact age of the ice. That's sort of how we got to discover that this ice even existed. And then part of my project and the previous project have been sort of to tease out the history of why is it there? How come we find old ice in a unique place like this?
Okay.
So yes.
Where did you do your PhD?
The University of North Dakota.
North Dakota. And your advisor had been working there for quite some time?
And he's been going to Antarctica for the past 10, 20 years, various places doing surface processing. Not necessarily old ice, but just understanding the landscape changes and past glaciations of Antarctica.
Okay. I think it's worth discussing the history of ice in Antarctica, like just broadly speaking, generally. A lot of people don't realize that Antarctica wasn't ice covered for all of time. Let's say it is the way Antarctica is today kind of formed in the last 5 to 10 million years or 30 million years?
30, it's like 35, 32, 35. I think the first if I remember this correctly,
Hmm.
and the first glaciers were formed, I want to say about 35 million years ago.
I think that sounds
And
right.
and then that's where you start having glaciers forming in the mountain ranges.
Hmm.
Kind of like you'll find a glacier in Sierra Nevada or stuff like that, right? On the
Yeah.
mountains. And then over time, that just expands. And I think we come into 32 million years ago is when we actually start having um, a big size Antarctic ice sheet. And then since then, it's pretty much been covered.
Okay. Okay.
And then there's been transitioning, larger and smaller, but it's been present pretty much since 32 million years ago.
Okay. Okay. That's great to know. So 30 to 32 million years ago. And for those watching, dinosaurs are extinct by 65 million years. We have 4.54 billion years of Earth history.
So
So you can
fairly
do,
recent.
yeah, so we could do the math, and 30 to 32 million years means Antarctica is a kind of a recent phenomenon. And the ice, so it's covered with ice. And something I learned reading your papers is that ice can't last very long on the surface, even under freezing conditions, because sublimation losses. So when water molecules move from the solid phase right into the gas, that
Yeah.
loss alone, let alone any melting, is
Yeah.
enough to shrink ice at a rate over a few million years that would actually make it
Yeah.
go away. So that I
Yes.
was like, that's crazy. So that would actually put a time limit like on
Which
that.
is why, Antarctica is actually considered a desert because it's so dry. And because of that and the sort of water pressure you're dealing with when you have a desert environment doesn't actually allow uh, for the ice to melt. So the only way, and especially in Oak Valley, which is a dry desert valley, you don't have melting, but you only have loss through sublimation. Or you have the glacier moving and essentially moving off the coast and into the water where it then melts and become parts of the ocean. But that's essentially the two ways you're losing ice. And it's
Okay.
actually not through melting. It's
Yeah,
quite interesting.
that is very interesting. It's almost like a constraint on the presence of ice, like a long-term constraint in a way, but the Ong Valley, as we'll talk about, kind of gets around that a little bit with the covering. But I do want to stay on this geologic history. So 30 to 32 million years ago, we have our first ice sheets that become permanent in Antarctica. They grow, wax, and wane. Now we have to
Yeah.
think about the northern hemisphere, Greenland. Now,
Yeah.
Greenland is another big continental ice mass. So they're like, it's kind of one of two big continental ice masses left on Earth because just 18 to 20,000 years ago, ice at the last glacial maximum was covering most of the northern hemisphere, expanded across the mountains. And I'm sure Antarctica was larger as well.
Yeah.
But Greenland, we can't find old ice in Greenland because the ice sheet, right, is only a few 100,000 years old in Greenland.
So it's actually, so the start of the Greenland ice sheet started 2.6 million years ago. And that's the beginning of the Pleistocene period. But Greenland is a lot more temperate
Yes.
relative to Antarctica, so it's not considered a desert. And you do have melting occurring. You do have warmer summers that allow for a large amount of melting. Underneath the glacier, you have much more warm-based glaciers, which means there is melting that occurring on the bottom of the glacier. So you're losing from the bottom, you're losing from the top. And because of that, you have a lot more mobility of the glaciers. And because of that, it's really hard to preserve the oldest layers of ice that was formed because you have deformation, you have melting, you have movement, and essentially all of that ice ends up into the ocean. So when you drill an ice core in the center of Greenland, you can go, or we have found to go back 400,000 years
Okay.
continuously in the layers. But I believe that's about the oldest you'll get there. Where in Antarctica, if you go to just kind of I don't know if you wanted to stay in Greenland, but to take it back to sort of Antarctica.
Go ahead.
That if you do the same in Antarctica and you drill down in the center of it, and where we have ice cores from Dome Sea, for example, we can go back 800,000 years. Mainly, I'm not an expert on this, but mainly because it's larger, you have that cold-based glaciers, which means it's kind of frozen to the bottom and not warm-based, where there's like a melting layer in between the ice and the bottom, the land, essentially. Then, so because of that, you're more likely to preserve.
I think you have frozen. If you can see me,
but because ice is still movable,
hear me,
it ends up into the ocean.
You may want to log
and
out
you still
and
have
re-log in
losses
if you can.
We have currently ice cores going back 800,000 years in Antarctica, like continuously, where we see the layers of season throughout.
This old ice is found in Antarctica. It's not found in Greenland. Greenland has formed fairly young, but in the Ong Valley in particular in Antarctica, your advisor had noticed this like geomorphic anomaly. So a bulge in a valley, you're saying. And this led him to investigate why that was. And he found that there was some old ice. And it turns out that this valley has the right conditions to preserve ice over millions of years, even given the constraint of sublimation. So that's the key for understanding ice over geologic history, that even if you don't melt the ice, for people watching, you can still dissolve, let's say, an ice cube in a cold, dry atmosphere simply because water molecules will sublimate off the ice. And you have estimates in here in your paper of those sublimation rates, I think. And that was kind of interesting to look at. It is surprisingly higher than I thought. So anyway, why is that bulge there? Why is that old ice there? And how did that bulge preserve it?
Exist? Yeah. And the key is sublimation. Actually.
Sublimation again. Okay.
So the scenario you were talking about is mainly if you just have clear ice, right? Water that have been frozen. There's nothing else in it. As a sublimate, it goes straight from being in an ice state to being in a gas state, and you essentially lose it. Now, if you imagine that you have ice, but it has a lot of dirt and debris in it, let's say 50% of it actually contains debris, then if you sublimate the ice, now the ice disappears, right? But the rocks and dirt and debris that is in that ice that is no longer there, that stays. And since you don't have water and you don't have, or these rock particles are larger so they can't be carried by wind, there is no means of removing the rock and the dirt. So that actually starts to accumulate on the surface of this ice that is disappearing. So with time, and you have more and more ice that disappears, the more of these rocks and debris that was in that ice is going to accumulate on the surface, and that is actually going to start accumulating and get thicker and thicker and thicker. And it comes a point where as that layer gets thicker, you're slowing down the sublimation rate, because now you have this boundary between the atmosphere and the ice. And then second of all, you're kind of blocking off the solar radiation that will heat up the surface. So you're actually preserving the cold ice underneath this thick layer. And I think about 10 centimeters or 5 to 10 centimeters, you start insulating the ice. And if you have this process occurring over 1 million years, in the case of Ong Valley, we actually see that like 60 centimeters are being built up over those millions of years, and that it's almost completely insulated and there's not much happening to it, which is why it can exist for so long, just being preserved, untouched, essentially.
Okay.
So the two things that kind of made it happen is the fact that we have dirty ice, so a bunch of rocks and debris in dirty ice. That's the key. And then we have sublimation. So those two combined actually cause the ice to be preserved.
Okay. In most cases, ice core scientists target cleaner ice for
Yes.
paleoclimate records. So like
Yeah.
Vostok and like you mentioned earlier, or
Don't
I think
see.
that's the core from Dome Sea. Yeah. And Gisp and Greenland, they're all considered
Be
clean
nice.
ice. Okay. That is another interesting part of this paper. That word in or first sentence in the abstract was debris rich ice core from a
Yes.
buried ice mass. Now, when I hear that, I'm a lake sedimentologist and I've cored lakes. And when there are rocks or debris in the way, it makes coring difficult.
Yeah.
And so, can you describe how one, first of all, goes about getting an ice core, how you do it, and then any problems from this debris, or does the core cut right through it?
Does not.
Yeah, okay. I thought I was like, yeah, I feel like this will be a very complicated process.
Yes. And the initial thought process was that from satellite images, we have kind of guesstimated the thickness of this ice to be maybe 100 meters thick, 50, 100 meters thick. And the initial idea was to bring this, what we call a wingy drill. It's fairly on a smaller scale, operated by a person, and can easily be moved around by a group of 3 or 5 people. And a helicopter can easily move this around and we can go to certain locations. And so the plan was to drill and get 100 meters of ice to bring home. And within 3 weeks, we got 10 meters of ice. And essentially, there are drill bits that are very specific for ice. And there's drill bits that are very specific for rocks. And it's really, really hard to make a drill bit that is good for both ice and rocks. So we kind of had both drill bits, and we had the driller, Grant Beckman, that had tested this out and designed it in the freezer of making dirty ice at home and try to see if what we could do and what would work, which is completely different than when we're actually in the field. Interestingly enough, we destroyed one of the drill bits within the first 2 days of drilling out of the 5 weeks. So yeah, it's a bit of a struggle. And some days we managed to get maximum 5 centimeters of coring that day for a full 12-hour workday, just because we hit some rocks. So we hit a combination of ice and rocks and constantly had to pull it up, switch out the drill bits, put a new one in, and
I see.
yeah. And sometimes we hit a clear ice sections and we got 3 meters in one day, and that was kind of the celebration day.
Yeah.
And then the next day we would get 20 centimeters. So very unpredictable in that sense.
And you were,
And I was going to say, sorry, for future
go ahead.
drilling, that has also been because more people are looking into drilling subglacial bedrocks and like that sort of lower area of ice where you have a mixing of rock. And a lot of people are looking into now how we can efficiently drill through both mixed media.
Okay. And as you're drilling this, are you living right at the core site?
Yes.
Yeah.
Living in tents. We have a little tent camp set up about 1 kilometer out to the side of the valley, and then we hiked into the drill site every day.
Over the ice hike.
Yeah.
I know I've hiked a bit on glaciers in Svalbard and in the Arctic. And I remember it's more difficult to hike across ice than I thought. Or maybe it is as difficult as I thought.
This is covered in dirt, right?
so
we are hiking on rocks. We actually you can't see any ice in the valley.
Oh, okay. I was picturing that these are like rock layers underneath the current snow and ice.
No,
So you're
there's
actually
barely
on.
Yeah.
I see
And
what you're saying.
because it's a desert, you don't actually have that much snow and precipitation throughout the year because it's a dry environment. So you actually don't have that much snow accumulation on the surface. And whatever accumulates disappears, sublimates within a day or two. So completely, it looks like it's completely ice-free, besides this huge buried ice mass underneath.
Besides this bulge of debris under, I've heard these being referred to. I know this isn't a moraine, but you can see these ice, like these debris covered or ice cored moraines in Svalbard, where the moraine is there. There's all this debris on it, but it's actually an ice core inside there, if I remember right. Like
Yeah.
because there's a lot of dry based ice in the Svalbard area, or cold based, I should say, cold based ice, which I do want to talk about a little bit more with you. But I want to know more about camping. I want you to describe this because most people in the world will never go to Antarctica, never experience what you experienced. You're one of the very few people in the world that have been there and taken the time to get there. So maybe if you can tell us about what's involved for you to get to that campsite. You said you lived in a tent. What was the weather like? Um, how long were you there? What did you eat? So maybe
So,
start with the travel.
yes. So the process of even getting there. So I was in North Dakota and we fly commercial airlines United to New Zealand in Christchurch, where the U.S. Antarctic program had a little center set up in the Christchurch airport, and where the U.S. Air Force operates out of as well. And so then we'll fly from Christchurch with the U.S. Air Force to McMurdo Station, which is one of the biggest U.S. stations in Antarctica. And then from there, we get most of our gear set up, all of our gear we get for the field. So tents and sleeping bags, kitchen supplies, everything is provided to us. We essentially, as the scientists, just comes with our own personal gear, and we get the famous red jackets provided in
Nice.
Christchurch for survival purposes. So we
Those are
spent
sweet. I've seen pictures of those.
they're very big and very bulky, and they'll keep you warm, but they're also too warm in certain conditions. Um, So then we'll be in McMurdo Station for, I want to say about 10 days, kind of go through all the proper training. This was my very first time going there. So even figuring out how to deal with setting up the tent. We're going through worst case scenario, like whiteout, windstorm. What happens if you lose your tent? How do you survive? All of these stuff. Get all our gear, get all of our food. And then in this case, we then flew deep into the continent and landed at a small camp that the U.S. Antarctic program had set up that year at Shackleton Glacier. And then that was kind of a hop where we were there for 2 days, I believe, just kind of unloading everything from the LC-130 plane that we flew, unloading that, repacking, and then everything was flown with a small twin otter to a nearby glacier. And then we were flown by helicopter to that area.
Like,
And then from that glacier, which was just across the ridge from Oak Valley itself, then from there, everything was helicoptered into Oak Valley. And I think
wow.
I did the math at some point, and it was, wait, let me pull this up. It's kind of funny, actually. I
Okay.
assume this is where you would do a pause.
Pull it up. I love it.
It is. I made like a fun talk about this. And I did the math. So we had about 10,000 pounds of stuff, in which we had 1,500 pounds of food. So we're 7 people that needed to survive for 5 weeks into the field. We were just dropped off in the field for the 5 weeks to survive. Nobody was coming in with food. Nobody was, supplying us with resources. So 1,500 pounds of food. Drilling equipment was 4,500 pounds. And the people and all of our gear, personal gear, camping tents, sleeping bag, all of this stuff comes out to be about 2,000 pounds. Sorry, so that's just people and gear. And then we had camping gear, which is 2,000 pounds. And in total, that took 6 trips with a twin otter and 12 trips with a helicopter in order to get all of the stuff to O'Malley.
That is probably the most intense
It
fieldwork
is,
transport I've ever heard and I've heard a
yeah,
lot of
yeah.
stuff.
It's not it's a complicated operation.
From the time you left, let's say you got on that plane in North Dakota and you spent your
Yes.
first night in the tent in Ong Valley, how many days was that?
I want to say 3 to 4 weeks.
3 to 4 weeks. Okay.
And
Wow. Oh
that
my God.
includes a weather delay and a boomerang. So a snowstorm can move in at any point in McMurdo Station. So we will take off for New Zealand, and then halfway through, we got a weather update that said that a snowstorm is moving in, and they would very much prefer not to land in a complete whiteout. So the plane actually turned around and we flew back to New Zealand, and then we had to wait for the
My
storm
God.
to be over. So that was an additional just 3 days hanging out in New Zealand, waiting for the storm to pass so we could do another attempt.
Man, that would have been, yeah, that would have stunk when you're on the plane. You're like, ready to turn around. You're like, no.
So just getting there can take a week,
Jeez. And
but it's
you're,
a journey, and it's worth the journey.
yeah, it's part of the job. Hello, everyone. I want to take a moment to remind you to please subscribe to this channel if you have not already, or like the video, or if that doesn't work, please leave me a comment below. Give me a suggestion about who should be on the channel next. Let's grow science communication. Thank you. I guess, you know,
Yeah.
and when you're in Antarctica, you don't have to worry about polar bears, right?
There's nothing.
This is something that I've found in the public is people don't remember which pole has polar bears and where the penguins are.
Yeah.
So just as a side little note, just to make this fun, but because I've been to Svalbard, like I said, we had to train for polar bears because they're small ice sheets on Svalbard, but they're there. And the coastal areas are where the polar bears hang. That's where we stayed, and they were there. Tons of polar bears. No penguins. But we do have there's puffins, which are very cute little coastal birds. Penguin-like, let's say. They fly, though. But in Antarctica, do you see penguins or any animals around you while you're camping?
Not where we are. We are that far inland that there is absolutely nothing. Biggest animal
Any
is
vegetation?
no. The biggest
No
sort of
vegetation.
animal organism you would find is a potential lichen anorak, like a little tiny micro algae in a rock. You could be lucky to find, and that is the biggest organism you will find, besides the 7 people around you. And that's within, I want to say within 500 miles of where you are. So there's nothing around.
That's like another planet. That's like Mars.
Yeah.
I don't think there's another equivalent, maybe like Mount Everest or maybe northern Greenland, but
no.
I don't even think that's like its own unique thing on Earth. And I've heard people say this kind of jokingly. It's like, why are we worried? Why do we want to go to Mars to settle when we have Antarctica? Like, if we're going to fly all the way to Mars to live on this cold planet with nothing on it,
might as well go to Antarctica where there's nothing there.
Just like we could just put a bunch of settlements in the Ong Valley and pretend like we're in a new place. I mean, no one wants to. I mean, I'll speak for myself. I don't want to live in the Ong Valley, and I think I don't want to live on Mars either. I like Earth, but I do think it's important to explore other places. Like, but yeah, and then so you're in the camp.
Just to kind of refer, there are penguins in Antarctica, but they're at the coast.
Yeah,
there are seals. There are birds. There are all of these animals. They're at the coast, and we are as far inland into the mountains you can get. So. It's because we're so far away from the coast that there's nothing. But there are wildlife in
You're in a
rocky... Just rocks. Rocks and ice.
Rocky, dry, icy landscape that the only other living thing besides people around you might be lichen, mossy thing on a rock, if that.
If even,
wow. That's some way to put it. And you're in a tent. So you all are in one big tent, or do you each have your own individual tents?
We have each our own individual mountaineering tent, and then we have a large, it's called an Arctic oven, uh, which is a larger tent where you can be, I want to say at least 10 people can be in there and in a tight fit, but you can cook, and we would have a whole setup, and we would have tables and chairs on the side. So that's sort of where we hung out together, kind of like a living room. And then we each had our own tent as being our rooms.
Did you have a generator that kind of heated and inflated the tent or
No,
anything like that?
no heat source.
Nope.
No, no.
What
It
was the
is
temperature like during the day?
anywhere, I do Celsius. So
You can say Celsius.
anywhere between 0 degrees, so just freezing, which is about 32 Fahrenheit, down to, I want to say, -35, which in Fahrenheit is also -35. So pretty much from freezing temperatures
Oh, really?
to -35 is kind of what we operate in, depending on
And
the
you were
wind,
there.
depending on the sun.
Yeah. Now, the weeks you were there, was it the austral summer, like
Yeah,
December, January?
yeah. Which is why it
Yeah.
gets
You go
to
down and
just below, like around freezing temperatures, like the 32 degrees Fahrenheit, because it is the summertime. And then if you have a cloudy day with a windstorm coming in, just generally cold, we could get the -30s.
Mhm.
And you either
Okay.
take off layers or you add layers, and that's sort of your only heat source. Or you pick up a shovel and you just start digging a random hole just to get warm.
Yeah. Okay. And then you, I don't see how could you dig in a hole in an ice block?
Well, it's dirt,
That actually,
but
it's like
and
I guess it'd
you
be the
can
dirt
dig
still.
into ice too. The
Yeah, I
harder
guess
it
it's like
is,
the
the
little
warmer
igloo
you get.
effect.
You're not digging for the purpose of digging a hole. You're digging for the purpose of being warm and like do work to your body.
Yeah, I see. Now, is sunny 24 hours a day when you're down there in December, January, right?
Yeah. So
So
no
you're
sunset,
sleeping in a tent, no
and it's
sunset.
just no
You put
sunset.
on goggles to sleep,
Yeah.
no sun. Yeah.
Actually, no.
When I
I
was in
didn't.
the
I
Arctic,
was not that smart,
no,
so I did not. I did not think that far, so I actually did not bring my goggles. So I would that just close my eyes, and that would be enough. Duck my head into the sleeping bag, and yeah.
gosh, because I remember doing the Arctic field work in the summer. I would wear those things because I remember if you got up like to go to the bathroom and it was like at midnight, it was as bright as noon. And like immediately, I remember a few times because I was in a cabin, but you could peer out the window. I would get
Yeah.
up in the middle of the night and go to the bathroom, just literally look outside, and immediately my whole body was like you could feel like the circadian rhythms, like what is going on? Like you're in, it's noon. Why are you asleep? And like you immediately start to wake up. So I learned they had the covers over the windows, that light proof
Yeah.
curtains or something. I just learned never to look outside when you wake up. Just keep your eyes shut, put the thing over your eyes, and you could sleep like pretend like it's dark outside. But I can, in a tent with no cover on your eyes, if I woke
You
up at like
you kind of
midnight
get
and it was that sun, you get
yeah.
used to it.
You kind of get used to it,
Yeah.
and like during the day, right? Like you use a lot of energy to stay warm in those environments, which means you also
Hmm.
eat almost twice as much. So you use a lot of energy. You have a full work day in the field where you're constantly moving, working your body. So most nights, like you're just after dinner, you're just absolutely destroyed and your body needs the rest. And if you
Hmm.
do that for 5 weeks, you do get into a rhythm. And we made sure that we're on the same time, like clock. Every single morning we woke up at 7, we had breakfast at 8, we were in the field at 9. That was standard procedure, just to give our body that like this is the time we're operating in.
Hmm. Okay, that makes sense. And what kind of food do you eat down there?
We were fortunate that we had a kitchen or like a camp cook with us. And so while we were in the field, all 6 of us research scientists, we had one that was a camp cook and essentially a camp manager that just kind of stayed put and organized everything for us, and she would cook us breakfast and dinner every day. And I must say, during my PhD life, I have never eaten that good during that period, and it was absolutely amazing food. She would make us pizza
What
from
kind
the
of dishes?
pan. For Christmas, we had steak and béarnaise sauce, and I believe it was like steamed broccoli, pastas, and shrimps, and everything frozen. Like nothing was fresh, but whatever frozen food you
Mhm.
could have. In the morning, we would get eggs and like eggs and bacon and sausage, or pancakes or porridge. Yeah,
Wow, you
delicious
ate well.
food.
That's way better than how I ate in Svalbard.
That was
Yeah.
better than most of my PhD food that I've had.
Jeez. Yeah, one thing I do remember when we did the camp is we had the person that made fresh bread. Because we were at like a station run by
Yeah,
like a Norwegian travel company, and they had cook there, but they made fresh bread every day, but everything was really limited. Like we ate kind of like the same rotation of food, and a lot of it was like stews and stuff like, yeah, like I remember a lot of like beef and carrot potato stews, or reindeer and potatoes,
yeah.
fish, potatoes, or mashed or baked. But like there is, and then drinks were limited to, unless you purchased your own, which were so expensive, you basically had tea, coffee, or water, and those were complimentary. And after a few weeks, a month there, those are the only three things you're drinking. And I was drinking water straight out of the lakes. Like I just would put a cup in
Yeah.
and just drink it.
Drink it.
And
Yeah.
so I was like, I really could go for like a beer here or something, or a Coke, or like a milkshake, or sugar. And do you get the cravings for like sweets and stuff when you're in the field, or like weird foods that you wish you could get that you don't have? I guess not when you're
We
eating that
had
well.
we had a lot of chocolate
Chocolate,
snacks, and
key.
yeah, I
Hmm.
I think
Keep
I
people happy.
ate. Yeah, but also it's a quick source of energy, and because you burn so much to stay warm, especially when it is the negative 30 degrees, like you actually do need it. Like I think I was eating maybe 3 to 4 chocolate bars and like half, like a full or half a bag of nuts every single day, which I would not recommend anybody do on a daily basis, and I would not do normally at home. And even with eating that much sugar and chocolate and candy and nuts, I still managed to lose a lot of weight in that 5 weeks, just because you're burning it all off because of the cold. Yeah.
It makes sense. Now, when you get to your core site, you're like a kilometer or so you hike out to the core site during the day. Now, kind of describe for people, what does an ice core look like? So you have different tips for going through ice and then rock. But overall, is this electrically powered, diesel? How does it work?
We have a generator that actually like produce energy to drill it, and then we have a container of drilling fluid, such that the drill doesn't. So it's a fluid that does not freeze in extreme environments, because if you do not have this drilling fluid, the drill bit would actually freeze on to the ice itself, and then you can't drill at all. Then the drill just gets stuck. So you need this drilling fluid that specifically do not freeze in cold conditions, which is also one of the issues, is that sometimes this drilling fluid, like either there wasn't enough or it got, I guess, too cold, and it actually froze, the drill bit froze onto the ice, and we were not able to drill. And so,
At all?
yeah, at all.
Just
Or until we
freezes
have
right in
like
place.
gotten the drilling fluid to the right temperature, and we could continue again.
Thought,
Yeah,
or get it to
yeah,
move.
yeah,
And do they come out? So I'm imagining a vertical metal pipe, aluminum, steel, that goes down. It's
yeah,
rotating,
yeah.
grinding away. Now,
It's
do you
grinding
get
away.
section?
Yeah.
Okay, go ahead.
And
Grinds away.
yeah, so we pull these like drilling rods that we attach, and as we go down, we add more and more to these rods, and then we pull them up, and we pull them vertically up, lay them down, and then we can kind of like slowly like tilt and scoop the ice out, and the ice comes out in these longer, smaller ice core sections, depending on the day, depending on breakage, depending on the conditions of whether or not it was ice or mixed medium or mostly sediment. Yeah. And we do have, and there's a figure in the paper as well, and I have some more pictures I can supply, where you see clear sections, and then there's a very distinct boundary, and then you go into 50% rock material. And then there's some sections where we're dealing with 90% rock material, so it's essentially just frozen sediment. And then a meter further down, you go into pure, clean ice with barely any sediment in it. So very
Wow.
variable throughout these 10 meters of ice. You go into these distinct layers.
Okay. Now, if let's say you had a full drive with the core, or like let's say you happen to hit a pure ice, how long of a section of core can be pulled out at a time? I'm imagining they can't be too long. You have to manage them, right? Like the length of the ice cores. Or can you take like a
That's
20-meter continuous core?
No, you would have to. That's a very good question. We never actually we never got to that point.
Yeah. I figure with the rocks in there, you would have been stopped. So like you're saying, you only
Yeah,
made it a few
and like
centimeters sometimes.
even it just naturally breaks into the sections. So when you're pulling it out from a rod that is 3 meters long, you would pull out just like a 2-meter section, and then another section of a meter would come out, just because it naturally broke in that boundary. So that's a very good question that I actually don't know the answer to.
Well, maybe maybe you could email me if you find out later. Because the reason I asked that is like lake core people, we can only get usually 1 to 3 meter. Like 3 meter for my equipment is the longest you can get, like a continuous. Then you're done. You have to pull it up. So if I was doing the ice core, I would have to take. And I assuming the 3 meters is like you hit no rock layers, like you're literally pure clay or something.
Yeah, which that never happened.
Yeah, and I think how thick are like Vostok, how many meters thick is that ice?
That is like 3 kilometers.
3 kilometers. So they can't be pulling up like meter
they're not.
chunks or.
No, but they're pulling up. I actually don't know the details of how exactly this worked, but I'm assuming they're pulling up sections. And then they're breaking, like, I would assume they would be breaking the sections, pull that off, pull the remaining up, break it, take it down.
Okay. But either way, you didn't get, with the place here at Ong, it's covered with debris. It made it difficult to core, but you're saying that ice preserved under that bulge in that valley, ice and debris, is about 10 meters thick.
So no, it is, we don't know the exact thickness of this ice. We can sort of guesstimate it from the slopes of the sides and sort of how the bulk shape looks like and what we assume a valley would look like and what the valley otherwise looked like further up. And if you kind of do these, you would roughly get like 50 to 100 meters thick. We only got 10 meters of ice core, just because we did not have enough time. We did not have the right drilling equipment to drill into these mixed media to get enough within the time period we were there. So we could, if we had stayed for a year or multiple months, we could have gotten a lot more, and we could have potentially gotten, I want to say 100 meters, but we were only there for 5 weeks, and we got as much as we could.
So of those 10 meters, I wrote the results. So the upper portion of your 10-meter core was dated to about 2.95 million years ago.
Yeah.
And that's significantly older than previous estimates of 1.1 million years, which I think was your advisor.
Yeah.
Coming up with that.
Or a previous PhD student, Ted
a
Bibby.
previous project to determine.
Yeah.
And then the lower part of that 10-meter core, your estimates suggest it could be between 4.3 and 5.1 million years old. In that at the bottom of that 10-meter core.
Yeah.
So let me digest this for a second. Vostok is kilometers thick, and it's only 700 years old at the bottom of that ice. Yet, long, covered with debris, there's pure ice below that is up to 4 to 5 million years old.
Yeah.
Okay, let me think about this for a second.
But two completely separate,
Yeah,
not at
these are
all
separate.
related.
They're not.
The
Good. Thank you
processes,
for.
the reason why the ice is there, it is probably as far from each other as you could imagine.
And I'll show a map with Ong and Vostok, just so we can see. I'll put it up.
And I
Pull it
have a
up
lot of
on here right now.
schematics that shows sort of conceptually how all of this works. So the Vostok is essentially pure ice. It's layers, right? So from the surface, you have current layers, and you go down and you just go back in time, year by year by year, and you can go down to 800,000 years continuously. In Oak Valley, what we're seeing is that, and maybe I should explain sort of what Oak Valley is and exactly how the ice got there. So you have the Argosy Glacier, which is the main or one of the outlet glaciers that essentially when the Antarctic ice sheet gets to the mountain range, it goes through the mountain range in these glaciers, and essentially all of these glaciers ends out into the ocean where it drains and it melts and become part of the ocean. But in this mountain range where it goes, Antarctic ice sheet essentially goes through the mountain range, you have the main glacier down valley, which is Argosy Glacier. And then you have these side valleys that are kind of perpendicular to the main glacier. And during time period of colder, when the Antarctic ice sheet was larger, these main drainage glaciers increases in elevation. And as that glacier increases in elevation, it has the possibility to expand into these side valleys. So the glacier is actually coming from the bottom of the valley and being deposited into the valley, which is very different also from any glaciers you would see in mountain ranges such as the Himalayas or in the Alps, in the Sierra Nevadas or wherever. And because the main glacier is down valley at a low elevation. So during period of glacial advancing and the increase in these outlet glaciers, it expands and it is able to expand into Oak Valley and up into Oak Valley, which is kind of contradicting to say because it doesn't flow up valley, but it kind of goes further up into the valley.
And we'll talk about that. That's the cold-based versus wet-based ice, right? If it can expand
it kind
freezing
of does happen in both scenarios or in both cases.
Okay.
Which means you have these events where the glacier has been able to expand into the valley. And then as it gets warmer, now during a warm period, the main ice sheets gets lower in elevation. But sort of because of the angle of the valley and because of sublimation and because of the debris-rich ice, because the debris has essentially been like mixed up into the ice during transportation and during expanding into the Oak Valley. And because you have this ice and debris and you have sublimation, you start sort of building this thin layer of rocks at the surface that start this preservation process that I talked about earlier. Essentially, during when the glacier is at its lowest elevation, not all of the ice that was deposited into Oak Valley actually gets out of Oak Valley and it gets preserved. And when you start having over millions of years, you have expansion, like increase and decrease and increase and decrease in the Antarctic ice sheet. And every increase, you have ice being deposited, and every decrease, you have the main glacier, the main Antarctic ice sheet lowering, but the ice does not necessarily get out of Oak Valley and it just stays up in Oak Valley. So what we're seeing in Oak Valley is actually these very distinct, and we call them drift, and it's essentially the leftover of these three distinct expansions. And you can kind of see it if you look at the picture from above. You can very much see these three distinct boundaries of these drift. And the previous PhD student from dating these, the exposure age, or like the surface of these drift, found that the oldest one was deposited, I want to say 2.6 million years ago. And the middle drift, where we find the ice that we drilled into, is, and I want to say, sorry, that the oldest drift currently does not have any ice in it. So it was believed to be deposited more than 2.6 million years ago. We don't find any ice below the surface, which means that all of the ice has essentially sublimated away over the millions of years of exposure. Then we see the middle drift, which previously was dated to be more than 1.1 million years old, which is what we drilled into. And then we see this very younger drift system from the last maximum, which is about 10 million years ago, and where there's currently ice as well. So we see these three expansions, and the general thinking is that when we drilled into the middle ice, then below it is still that initial older deposit, and then we have the middle ice, what we call it, which is a later deposit that was deposited on top of it. So now you have these two layers of glacial expansion or glacial advancements on top of each other. And the theory is that we drilled into the top one, dated that one to be 2.95, and then actually are drilling into that second and older, and that we date to be 4 to 5 million years ago.
Okay.
So that's sort of the general sort of history of Oak Valley, which also means that because it was the whole blob of ice was deposited at one instant, right? It's not layers that have built up over
I
time,
see.
like the central ice or the Dome Sea ice core, right? So we don't actually see layers. We can't extract day by day history or year by year history. What it is just a snapshot or a window into a one specific time period in which the Antarctic ice sheet expanded and was larger than it is.
Okay. I would have to say that's a fairly complicated geomorphological history for a valley. And I'm glad I recorded that so I could watch that over again and think about it, because that does seem complicated. And I think that's a good segue that you mentioned the layering in the ice, the old ice there, because my next question is, we get these ice cores why do we want to get an ice core? What's the point of getting ice cores? So maybe tell us about what can we learn from gathering ice cores and analyzing their composition, both the water and the gases preserved in them.
So regular ice cores, when you have these layers, and like some ice cores are fairly young. For example, up in Greenland, or if you drill up in the Alps, or if you drill up in Alaska, you can get very seasonal. So the past 100 years, for example, you can get very seasonal layers of past climate conditions and volcanic ashes, deposits. And once you go further back, you get more.
Your records get squeezed.
Your records get squeezed, and there's like layers gets lost,
compacted.
And you can compacted, and you can't really get seasonal data, but you can get general information of how the atmosphere have changed, the conditions, the temperature. You can look at the Delta 018 data, deuterium, oxygen, CO2 levels. All of this stuff is all preserved in these layers, and we can kind of get that detail going back to essentially the age of the ice.
The ice formation.
Yeah. And that sort of and that continuous knowledge we can get from Dome Sea and go back to 800,000 years. And then beyond that, we don't have any direct measurement of the atmospheric conditions, which is why there is a large interest in current drilling projects, both by the Europeans and the Americans, to go find ice that goes back 1.5 million years, because now we can, extend our knowledge going further back in time.
Okay, I think that's a good point. I kind of just want to stop and think about this for a minute now. So you're saying ice cores can essentially tell us about Earth's past climate, like temperature, moisture, dust sources, and they literally accumulate on the ice cap. They're incorporated as firn and ice, from snow to firn to ice as they get compacted. And then these layers in certain areas of the world, like Vostok and in some places in Greenland, they'll actually accumulate layers for a long time. But as the weight of that ice builds up, it actually compacts the ice in the deepest section, almost limiting the ability to look at those layers, or almost compacting them together.
Yeah, yeah. Sorry. Yes.
Yeah, and
Good.
okay. And so this is kind of like a big reason why we want ice cores, because before instrumental records and thermometers and rain gauges were invented in the last couple hundred years, we just don't have any idea of Earth's even recent geological climate. We have at least no measurements, observational measurements from equipment. So we have to use proxies, and ice cores just happen to be some of the most potent, because they can get us those annual layers. They also sometimes trap bubbles, which we can analyze the gases in the bubbles to get direct indication of the past atmospheric composition. And this is that famous graph where it shows the CO2 going up and down, and the proxies for temperature, like deuterium and oxygen isotopes, are tracking or related to that CO2. And then we understand that CO2 and temperatures are closely related through Earth's geologic history.
Yeah. And ice cores, there's many ways we can get information. As you may know, like lake sediments, caves, just general information that most geologists have studied. We can get proxies for what the atmosphere was like, or what the temperatures was like. But ice core specifically, if it contains air bubbles, right, that air bubble is a direct measurement from the atmosphere at that time. Where all the other ones are, we call them indirect, where the ice core is actually considered a direct measurement. So that's kind of uniqueness with ice cores. So we have a lot of information going back about a past climate, but not directly measured.
Not direct bubbles of gas measured. We can infer things with, like tree rings, for example, temperatures or precipitation in spring. We're not actually measuring precipitation, whereas the ice core has the gas bubbles in it that we can actually measure. And those gas bubbles are actually formed when the snow on the ice cap compacts down over time, and it actually traps the bubbles of gas in it, correct? And there's a whole process on there. I'll show maybe a side cut of a ice sheet image or something, so you can look at that.
So the uniqueness then is it's really hard to go back and find direct and continuous measurement going back more than the 800,000 years, because those clear ice cores, we drilled to the bottom of it, and that's the maximum age that we get. So what we have sort of tried with this specific ice core is we can't get continuous information out of it, but we can potentially get snapshots and fill in blank spaces going back. So we could potentially, right, with this, we know that the top layer of the ice is about 2.95 million, right? And we do see air bubbles in this ice. And it might not be continuous, it might be sort of a mixture, but this is the closest we can get to a direct measurement of atmosphere that was at least 2.95 million years ago.
Okay.
And we do actually have these measurements. So we have detailed Delta 018 measurements of the ice core, attempted to do CO2 analysis on this ice as well, all of which hopefully is going to get published within the near future.
That was going to be my next question. I do want to get to that, but I want to first, before we, if you're allowed to talk about it, you could talk about whatever you want and what you feel like you are allowed to talk about. I know co-authors, sometimes you have to get consensus.
It's just a
Yeah.
matter of when I have time to write it all up and also sit down and
Okay.
understand. So yeah, there's a,
Okay.
because we don't know, right? Like the measurements that we have, there's nothing we can compare it to really.
Yeah.
It doesn't follow any traditional ice core that otherwise exists out there. So just trying to figure out the puzzle pieces and how it all matched together is quite complicated. I haven't sat down yet and figured out all of the pieces, but we do have the measurements and we're trying to figure out how it all matches up and what story can kind of Oak Valley tells us of our past.
Okay. And so the Vostok core, again, 700,000-800,000 years. So there's this huge interest among the scientific community because Vostok is older than the Greenland cores, GISP and other ones too. And there's other shorter ice cores around Antarctica, but Vostok is kind of the gold standard of that layered ice, clear ice. Now, there is a search, you're saying, all US, European, for older ice so we can maybe find bubbles and other chemical proxies in that ice to tell us about directly the atmosphere before 800,000 years ago. We don't know. And you're in the Ong sheet, or in the Ong ice, I shouldn't say sheet, ice. Again, to recap, it could be 2 to 4 up to 5 million years old ice. Now,
Yeah.
the bubbles that you have captured, because you again say it's not layered, it's the oldest ice is sort of a homogeneous mass, let's say, or deposited relatively rapidly.
Yeah.
But there are bubbles in that homogeneous mass that are preserved. And they've been in there since then. Okay. And now those bubbles, when do you think they are dated to? Again, in that range I just gave you. And how did you date that? Date that
So
ice?
The bubbles we have afterwards to do some analysis on, and this is not necessarily my specialty. So we have sent the ice out to other people that have dated for CO2, that have dated for oxygen, all of this stuff. So we have the data that we're sitting on. None of that gives us the age of the ice. The age of the ice was dated through the rocks inside of the ice, which is also a unique situation. And because it is so dirty, and because we do find rocks mixed in from the surface all the way down to the bottom, we can use these rocks to actually get estimates of the ice. And the way this works is that it's called cosmogenic nuclide dating. And it's based on the concept of specific rare isotopes that we call cosmogenic nuclides that are only being produced in a rock when it's at the surface. And so it's the rare isotopes, and we have beryllium-10, neon-21, aluminium-26 used. We also have zinc carbon-14, we have chlorine-36, and helium-3. So these are the cosmogenic nuclides. They're rare isotopes, and they're only being produced when a rock is at the surface. So when a rock...
Why is that? Why are they only produced?
They're produced by cosmic rays. So that is high energy protons that comes from outer space, and they constantly bombard Earth. So it's high energy protons that is hitting Earth's surface. And when they hit a rock at the surface, that energy causes spallation reaction that produces these specific isotopes. And if you go further down below the surface, these high energy protons does not penetrate much below the surface. So the surface essentially shields any production to occur, which means if you have a rock that have never been exposed at the surface, you essentially won't be able to measure any beryllium-10, aluminium-26, neon-21, helium, chlorine-36. You'll measure some background noise based on some other processes that happens. But essentially, very simple assumption is that a rock contains none of these nuclides. And as soon as the rock gets to the surface, it gets exposed to these cosmic arrays, so high energy protons, neutrons. Now you start producing beryllium-10, neon-21, aluminium-26. And the longer the rock sits at the surface, the more of these nuclides there's going to be. So if you take a rock, you measure how much of these atoms there is, you can relate the amount of atoms that you measure to the time that the rock had been there. So that's sort of the general concept
Hence the
of
word
exposure dating.
of how it works.
Yeah.
Yes, hence
Yeah.
the word exposure dating. So it's the
not the
length
dating
the
of
rock
the rock
debris
itself.
has been exposed.
It's not the dating of the
Yes.
rock itself. It's the dating of when the rock arrived at the surface and how long it's been there. And we use this a lot in glacial settings
Okay.
because a lot of glaciers causes rock coming from underneath the ice sheets that have never been exposed. It kind of like scrapes and bumps and kind of loosens the land underneath it. And eventually those rocks during glacial advancement get pushed up at the front of a glacier, and it causes what you talked about earlier, these moraines or glacial deposits. So the general concept is that none of these rocks were ever exposed before. The glaciers comes and scrapes it all from the bottom, and it pushes it up to the surface. And as the glacier then pulls away from the area and during glacial and deglaciations, then it leaves this pile of rock. And if we exposure date using cosmogenic nuclides, we can figure out when that pile of rock was deposited, and we can relate that directly to the time that the glaciers were at its maximum extent and had reached that level. So we can do this simply at the surface, but because of these cosmic rays, high energy protons, they kind of losing their energy as they hit material. So when they hit the surface, they actually kind of lose their energy. So they still travel down into the surface, but they don't reach as far down. And the production of these cosmogenic nuclides becomes less and less as you go down. So if you have a surface that have been exposed for, let's say, 1 million years, you're going to have a large amount of cosmogenic nuclides in the rock at the surface. But if you measure the rocks going down below the surface, you're going to find less and less. So you can kind of have this profile that decreases with depth. So the idea with pulling up the ice core that have a bunch of rocks in it, we can measure the cosmogenic nuclide concentrations in all of these rocks going into the ice, and we can build a model that predicts based on an age, sublimation rate, erosion rate, what the nuclide concentration should look like after X amount of millions of years. So we built this fancy model that essentially predicts the nuclide concentrations, and we run it through an optimization, which means we are optimizing for the age, sublimation, and erosion rates, and we find the best fit between what we measured and what we're predicting. And it's through that way that the best fit for sections of this ice course essentially is found with an age of 2.95 million years. Now, the interesting part is that the bottom of the ice cores and sections of the ice cores have a lot more of these concentrations or these nuclides than we expected, right? I just said earlier that you're going to have less concentration as you go down. You're decreasing. So in a simple scenario, you should not be able to measure twice as much deep down in the ice core because there should be a lot less of it. So
Yeah.
we're doing all of this fancy modeling, we're predicting all of this, and we're just like, wait, but this doesn't explain why we suddenly see an increase in concentrations as we go deeper down. And so then that kind of got us thinking of, well, something must have happened for these rocks that are deep down, like somewhere in the past, these rocks must have been at the surface. So this is where we start, this is where it kind of gets complicated. This is where we start dealing with burial, right? So you would have had a rock that had been at the surface, it have accumulated concentrations of these nuclides, and then you bury it. So now you're shielding it. So there's no more being produced, and you're slightly losing these because they're radioactive, so they have a decay. So you're slightly losing some of it. And the fact that we see these higher concentrations at the bottom of the ice cores tells us that these rocks must have been at the surface accumulating at some point in the past. So within our modeling, we're including burial scenarios, which is where we're getting this 4 to 5 million years ago. And that matches up with the general observations of these 3 drifts that we see at the surface in Oak Valley, where the first drift that was initially dated to be more than 2.6 is actually 4 to 5 million years old. That this middle drift, so the second advancement, came in and override some of that old ice 2.95 million years ago, and essentially starting to bury a previous surface. So yeah.
And then
Right?
that previous surface must have been, I'm following. I mean, I really appreciate how you're talking very clearly and slowly. Even it is complicated, but so that layer that was buried with higher amounts of cosmogenic nuclides must have been exposed at the surface for a long time before it was covered again to be able to take up that much, because like you said, it was
that
subsequently
difference, right? That time difference is the difference between 2.95 million years and then 4 to 5 million years, right?
Okay, 2 distinct stacked ice masses of different ages is kind of how you describe it, but they're layered on top of each other with a debris layer between them, essentially, right?
Yeah.
And then a debris layer on the top, debris layer in the middle, ice, and then below that, really old ice that's somewhat clear.
Yes.
Okay. And I was also, it's impressive to know that you can use 3 different nuclides for dating. So they're kind of in a way independent lines of evidence.
They're completely 3 different independent. They each have their own production rate. So one is going to be produced much more rapidly than the other one. And that's actually a benefit. So in a simple concept, we can take one rock at the surface, we can measure one nuclide, and we can calculate the age. If we take one rock and measure 2 nuclides that have 2 different production rates, then the ratio between them, the 2 amount that we measure, we can tease out erosion rates. So now we can start getting information about surface processes, because we can calculate by the age, there should be these 2, the ratio should be this much between them. But if it's not, then another process such as erosion rate must have caused that ratio to change, and we can quantify the erosion rate happening based on this ratio difference, essentially. If you add in another or like a third one, now you can get a lot more details, right? So we use, and it's really beneficial in cosmogenic nuclide dating to have at least 1, but 2 or 3 to tease out all of these geological processes. And especially this becomes interesting when you do burial dating. So if you want to tease out information where the rock had been exposed, it's been buried, and it's been exposed again, because they're being produced at 3 different rates. But as soon as you bury it, the nuclides are being decaying, so they're being lost at 2 separate or 3 different rates. And the ratio, if you have 3, now you have 3 different ratios, and essentially all of these ratios have to tell the same story. So you're just adding in constraints at the age, burial, and erosion rates, which is why we want to measure. And if we could measure 5 or 6 or 7, that would be great. And we can't. Yeah, within the mineral that we are dating, of all of these various nuclides that exist, beryllium, aluminium, and neon 21s are the ones that are being produced specifically in quartz. Now, if we had another mineral, this is a little bit more details, but if we had another mineral such as a darker Pyroxene, now we would have helium-3, beryllium-10, chlorine-36 being produced. We can measure those 3 nuclides, but we're sort of limited in quartz to these 3 nuclides.
Okay. How about OSL dating? Any use down there at all, or just not attempted, or a reason why it doesn't work?
That is,
Optically
yeah,
optically stimulated luminescence.
yeah, it's when stuff haven't been exposed to lighting, right? I'm not quite
Yeah.
familiar with it.
It's almost the reverse, I think.
Yeah,
It's how long it's been in the dark versus
how long it's been exposed to the surface.
Yeah. Either I don't want to get us too lost in that, but
yeah, no,
I guess
it does not work.
it doesn't
works
work.
for certain, it's yeah. It would
And
not.
radiocarbon only works back to at the most 50,000 years, and we're way beyond that.
We're
so
way
we
beyond
need to
that.
use
Even so,
we need to use something
even
different.
aluminium, so aluminium 26 has and that's depending on the decay rate. So aluminium 26 have a decay rate of, I'm going to get this wrong, 300,000 years. And the general rule is that if you take the decay rate and you multiply it by 3 to 5, that is the maximum exposure age you can get out of it. So for aluminium, that will give us like about 1 million years, like 1.5 million years. That's when the signal starts being saturated, and we actually cannot get any information out of aluminium beyond that. For beryllium, that becomes about 4 million, 6 millions is when we start seeing the signal being saturated. Neon 21 is stable and do not have a decay rate, so we can use neon 21 going multiple, like millions of years. We just get to a point where a rock just doesn't survive longer than like 15 million years at a surface, then like the rock is not there anymore.
The rock's not, it's I think that's
like,
actually
I think the oldest surface, and I'm currently working with some of these rocks, like the oldest exposure age that we have ever dated on Earth is I think it's 11 million years. And beyond that, we just don't have a rock that have survived at the surface for longer than that. So that's kind of the limiting factor. So yeah.
Now, with those 3 constraints on your ages, you are pretty confident that old ice with the bubbles in it is well dated or constrained as best as you can. You're confident that
the 2.95. Yeah, the 2.95 is the bottom ice core due to the whole complexity of, or the bottom section of the ice core due to the whole complexity of the system and what we can do with the cosmogenic nuclides, the dating, the modeling we've done. And it's very hard to tease out a specific age, which is why we're reporting the 4.3 to 5.1 That's sort of the best sort of
Yes.
information we can tease out of that.
Okay.
So yeah.
Now, in that ice, that 2 million-year-old ice, and you said you have analyzed bubbles of gas, which represent atmospheric concentrations in these layers. Now, what would be your best guess for the age of those bubbles? I mean, you
We
said 2
don't
million, but if you don't have a good age, and then what is
know.
the
So like we can measure the CO2, and that,
okay?
as far as I know, just gives us the CO2 concentration. And we have sent off the ice for argon analysis, which argon could provide an age. As far as I know, that has not been analyzed and done yet. So yeah.
I see what you're saying. So then you have those constraints in the debris layers, but you're kind of but between those layers, you don't have much of an idea of the specific ages of the ice, like down to, let's say, an error of less than 100,000 years or something.
Yeah.
Yeah. Okay. What were the concentrations of the CO2 in those bubbles? We
God,
know that
I haven't looked at this in 3 years, so please don't
if you
ask me.
can, oh, okay, if it's convenient for you to pull up, I would be more than willing. If you can share it, I don't know.
Well, I
It's
can
okay if
pull
you
it
can't.
up, but the thing is, understanding the system and like there's other processes that potentially could cause the gas that we actually measure, right? It's not 100% a deflection of the atmosphere from that time period, because essentially those air bubbles, right, as we talked about, they were formed in the center of the Antarctic continent. And then over millions of years and millions and millions of years, that has been deformed under the
Mm,
Antarctic ice sheet. Then it has moved
got it.
500 miles going into the mountains. Then it's been squeezed into the mountains. And then the glacier has expanded, deposited all of it 2.95 million years ago. So the ice itself could have been formed 6-7 million years ago, like 3 million years ago in the central continent. So we're only dealing with when the ice essentially got deposited but not formed, if that makes a difference. So we can measure the gas and the air bubbles, but whether or not what time period that actually relates back to or how that whole system works is beyond the knowledge that I have, nor that most other people have.
Okay.
And we've
That
talked to
makes
some,
sense.
like the person that measured this is, I believe it was, I want to say Ed Brook.
Okay. I've heard of him.
I
Ed
think it
Brook.
was him. I could be wrong.
A couple years.
It's been a couple years, and I think the person that measured this was measure CO2 in ice cores, and I used the continuous ice cores. But because this situation is so unique, what I remember from emails back then is like, here's the results. I don't really know what any of this means. And then I opened up the file, looked at the results, and great. I also don't really know what this means, which is why the paper is not written yet.
Sometimes that happens. You're like, what does this mean? And I don't know what to do with it yet
Yeah.
and how to publish this. The
Yeah.
reason I'm interested in
Like it's
knowing
super
it, or
interesting, but like it's just, yeah,
because
it's very,
if you could be like confident that, hey, that air bubble was from 1.1 million years, or let's say air bubble from anywhere before Vostok,
yeah,
essentially, and you knew that bubble was that age, you could tell us what the CO2 is, because today I just checked is 427 ppm in the current
yeah,
atmosphere for
yeah,
CO2. We're way above the
yeah,
400 level. The
yeah,
last glacial maximum, if I remember right, is something around 200 to 250 parts per million at the coldest part. So it would just be interesting to see where you would be on that range. And because I know back in time, as we go through the Cenozoic, so after the dinosaurs went extinct, it was a greenhouse world in that early period. Before 30 million years ago, there was really no permanent ice, at least no evidence for permanent ice on planet Earth. So 2 million, 3 million years ago is kind of right in this gap, this Pleistocene transition. Well, not that, but right at the Pleistocene
It's
boundary.
yeah, the mid-Pliocene warming period
Mhm.
is about 3.2 million years ago, and that was the time period where we had similar CO2 levels as we do now. And so there's a lot of interest in this period to figure out, okay, what was the Antarctic ice sheet doing during that time period? What do we know about the CO2 levels, the sea level rise, all of this stuff? And essentially, all of this comes into predicting what's going to happen in the future, right?
Right.
Is
That's
New
what I
York
was
going to be
interested in.
underwater? Is Miami going to be underwater? Are we going to flood the
Yeah,
world essentially?
I would want to know, like, is the CO2 level where, like where is it on there? Is it above 300? Is it above 350? Is it 400? If is it above 400? But until you publish and figure it out, we'll leave that mystery. Maybe if you publish a paper, I'll have you back on to talk about it when you feel more confident discussing.
We can agree to that, yes.
Mhm.
But yeah, we're dealing with buried ice masses in Antarctica that are formed through sublimation of these debris-rich ice. There's other groups, and one group coming out of Princeton, which is John Higgins lab, and they're working in a different part of Antarctica in what we call blue ice regions, and they have done some drilling, and they have published the 2.7 million year old ice got published, I want to say around 2021, 2022, around that
I
time
need to look that
period.
up.
And and then I can send you the paper afterwards if you want.
Yes, please send that. I'll pull that up for
And
this.
then they have continuous done drilling over the past couple of years now. And I went to an ice core conference, and their last dating that they presented at the conference,
There.
there's and completely different system, completely different settings, and how the ice got there and all of this stuff. They also have pockets and screenshots of sort of ice going back couple of million years, and they're continuing to working on that too. So yeah,
Love to talk to somebody from that group. Maybe when you send the paper, it'll inspire me to
yeah.
look up some co-authors or authors to see if they would be interested in talking.
I know there's
So,
a girl or a woman kind of similar stage, like postdoc student, or not student, but sorry, postdoc, that kind of similar stage as me in career, that I think could easily speak on that.
okay, I'll be very excited to talk to them. Now, part of the mystery of ice sheet formation, and we're stepping back and looking broad scale interests, mysteries of the paleoclimate world. There's this kind of famous transition called the middle Pleistocene transition. And so this happened, I think, around 500,000 to 700,000 years ago, or something along that line. I double checked, but I think that was about it. The timing is kind of debated. There's a window of when the transition happened, but it's something around that time. But what happened was the glacial cycles on Earth in the late Cenozoic, there has been this fluctuation of glaciers.
Yeah,
They expand and then shrink. They expand and shrink. And this seems to have happened on a 40-ish thousand year cycle up
yeah,
until the middle Pleistocene. Then over the course of a couple 100,000 years, that oscillation, we can even sound like the frequency of Earth's
yeah,
ice variability shifts to 100,000 year cycles.
yeah,
40,000. This is weird because most of what we think drives glacial cycles is on 1,000-year time scales is Milankovitch, which is
yeah,
the changing in the distribution of sunlight in response to Earth's orbit, the wobble precession, the how circular the Earth's orbit is versus oval. But there isn't those solar cycles. There's nothing at the 100,000 year band that stands out. There is a solar cycle, let's say a Milankovitch cycle, that does come at the 40,000 year band, but nothing at the 100,000 year band. So what drove that change in the middle Pleistocene is a huge question driving a lot of research, and getting ice that spans that period, like maybe these people at Princeton have, they will be able to capture that in a way we have never seen before, especially if we can get direct measurements of the air to get at that. Now, what is your
And I have
opinion on this middle Pleistocene transition? Do you know, what is the current thinking on what drove that change?
that's a very good question that I don't think I have the answer to.
I think that's why it's the mystery. It is
Yeah,
very weird. I think I've
yeah,
heard like feedbacks in erosion across the, like removing the regolith, like the surface rocks off of the continents of North America and Europe and Eurasia, somehow changed the cycles, because it had to, like when it ice first descended upon the northern southern hemisphere between 30 and 3 million years ago.
yeah.
There's lots of thick rocks over the continent, and those, once the glacial ice started expanding and contracting, started actually scooping off that regolith, and then eventually it like scoops off the like resistant ones, and then below that it slides faster or something like that, and then
Yeah,
that, or it actually it erodes the fast stuff and then gets to the hard bedrock underneath and slows it,
and you got
and then that, like that's the only, I think, only explanation I've ever heard, and even that I had a hard time saying, and even that just doesn't sound very convincing
no.
at all. So I don't, and it is the mystery, so that's why it's so imperative, like there needs to be an ice core record
Yeah,
to look at that and to see what is CO2 doing.
what?
Is
Yeah,
this 40,000 year cycle? I think in the ice core, or in the ocean sediment cores, I think you can still see that 40,000 year cycle, because that's that Zakos paper in 2001. He did like a compilation at first, and then there was another recent compilation of sediment core temperature records. They find that 41,000 year cycle is like, goes back pretty far.
yeah.
I think like 2-3 million years. Like there's that Wikipedia figure, 3 million years of Earth's temperature, and I think that's a compilation of ocean cores.
Of course.
But that's the thing I was wondering is, is there some kind
What?
of, yeah, is there some sort of atmospheric signal there that we could tease out to explain this
And that's
transition?
gonna be really hard, and especially with ice cores, because most likely we won't find continuous ice cores going back. We'll find like snippets of old ice going back to those periods. And again, it's small puzzles that we're trying to like get a bigger picture from. And I think it's
Mhm.
going to be really, really hard to kind of understand what exactly all the details of that is. But I think what we're trying to do now is just like, what information do we even know from certain periods of the Pliocene? Because right now there's really not much. And I have a figure as well where we kind of have the general knowledge of the glacial history of the Antarctic ice sheet during the Pliocene period. And this is taken from small, I think, deposits or cores from just offshore of the Antarctic continent. There's like some records of glacial deposits up in Patagonia, sort of on the southern hemisphere, that kind of gives us information of what the Antarctic ice sheet have been doing. D. Shepard in 2014 kind of did a summary of what we know from that period from Antarctica. So the Pliocene period goes from 5.3 to 2.6 million years ago. And around 4.8 to 4.9 million years ago, we have this cooling period, glacial advancements, which is in the early Pliocene. And then after that period, we go into this warming, like slowly warming period that kind of peaks around 4.2 million years ago. And then that goes into a cooling period that essentially end in the MIS M2, 3.3 million years ago. Then there's this abrupt warming of the mid-Pliocene warming period that we call it, that expands from 3 to 3.25 million years ago.
Mm-hmm.
And so that's the mid-Pliocene warming period, where CO2s were similar to what it is today. And global temperature is about the same as what it is now. And so specifically, we're very interested in that period. And then essentially the Pliocene ends 0.6 million years ago, and it ends in a cooling period, which initiates the Northern Hemisphere glaciation. So essentially, this is where the Greenland ice sheet starts forming. So that's
Okay.
sort of the outline of what we know about that glacial glaciations that occurs during the Pliocene.
Yeah,
And
the
of course,
patterns.
somewhere in there's a lot more patterns, but we just
Yeah,
don't know.
we don't know.
This is the major coolings, the major warmings that we have found records of. And if you look at sort of where Old Valley comes in, because in order for the ice to have been deposited 2.95 million years ago and 4 to 5 million years ago, the Antarctic ice sheet must have been larger. And specifically, the Antarctic ice sheet must have been, or at least locally, must have been 200 meters higher in elevation in order to have reached into the area in Oak Valley where we're currently finding the deposits and finding the ice.
Okay.
So in order for Oak Valley ice to have been deposited during these two periods, the local ice sheet elevation must have been 200 meters higher, which in order for that to happen, most likely a glacial advancement, right? It must have been a cooling period where the Antarctic ice sheet has advanced and expanded. And if you look at this grand scheme of where that falls in with the period, that older ice, so the bottom of the ice that we find to be 4.3 to 5.1 million years ago, fairly large uncertainty. I understand that. But that kind of falls into that early Pliocene period that we have records from the mountains of Patagonia, or
Okay.
the Patagonia mountains of 4.8 and 4.9 million years ago. So there's kind of records that like this kind of lines up with previous records that says early on we had an expansion. And then interestingly enough, the Oak Valley of 2.95, and if you take that uncertainty of I believe it's 200,000 years uncertainty, right? Like plus minus 200,000 years. Half of that falls into being in the mid-Pliocene warming period, and the other half falls into being in that cooling period scene. So that actually lies right at the boundary and the end of the mid-Pliocene warming period, in which the uncertainty actually lies within the warming period and the other half lies within the cooling period. So to go into details and say specifically whether or not the Antarctic ice sheet was larger or smaller during that period is like, we can't really confidently state whether or not we did observe a larger ice sheet during that time period or if we did not. Because of that perfect uncertainty lies right halfway in the cooling, halfway in the warming period. The kind of cliffhanger, disappointing results in this whole grand scheme of teasing out what exactly is happening to the Antarctic ice sheet during this time period. Mm-hmm. But it is kind of like the more we do this, the more information we get. Mm-hmm. Eventually, we'll get there. But one thing that's really interesting and I don't kind of make sense to talk about now is that so we had a master student actually look into, okay, there's many valleys in Antarctica. The whole mountain range, right, expands thousands of kilometers. Oak Valley can't be unique, right? It can't be the only place in all of Antarctica where we just happen to find this. So we had a master student, Miranda Shanks, actually look through all satellite images of Antarctica, of all the land, and she found about 42 valleys that still, similar features, have this bulging shape in the center of it. And based on just knowledge of what we know about Oak Valley, we have kind of constrained and limited the amount of site to about five, I want to say 10 or 7 or 10 locations in Antarctica throughout the Transantarctic mountain range where we see very similar features as we do in Oak Valley. And we see very similar bulking shape and elevations of where we see these bulking shape that match up with Oak Valley, indicating that these 7 to 10 sites potentially have these same deposits from, hopefully, from the same time period.
Okay.
So kind of some future projects that we're hoping to get to would be ideal to go to these 7 locations, drill into the ice or collect surface samples and figure out, okay, were these deposited the same time as Oak Valley? And can we now start teasing out throughout the Transantarctic mountain range what the Antarctic ice sheet have been doing at different locations, right? Because right now Oak Valley is the information we have is very local to Oak Valley. So if we can start like discovering these other valleys that we can get information on from this time period, then now we can sort of start looking at the bigger picture of the Antarctic ice sheet during that time period. But that's going to take us years in order to even get to those valleys. And as I talked about in the beginning, it's a almost logistical nightmare to figure out how to get a couple of people to camp out in those valleys and dig for rocks.
Can only imagine. Yeah. So we've been talking for a little over 2 hours, and I kind of want to get into maybe a little bit, just a random curiosity question that I want to start this idea. Maybe you'll tell me other people have thought of this, but maybe it'll start with you and you could talk to your colleagues about it and see where it goes from there. But the cooling off of Earth in the Cenozoic, especially the late Cenozoic, like we're talking about, middle to late, and you kind of talked about it, but it seems to be driven, overall the cooling seems to be driven by, first of all, the changes in the currents around Antarctica, with like Drake's Passage opening up is one thing I remember. And so that allowed for this Antarctic circumpolar current to essentially thermally isolate the South Pole from the top, whereas the Gulf Stream brings a lot of heat up into the Northern Hemisphere and exchanges it there before it makes it deep water. That's one thing that led to the cooling, or one idea of Antarctica, is that opening of the Drake's Passage and the current there. And then the other one is the weathering hypothesis, where the Tibetan Plateau elevates like 5 to 15 million years old. The idea is that it led to enhanced chemical weathering and an overall slow drawdown in CO2. And I know that is controversial, and I think some people have found issues with that. But those are like the two main drivers of temperature changes on, let's say, million-year timescales. Because when we're below that 1,000-year, we're in the Milankovitch forcing more important, superimposed on these longer trends. I want to throw a new thing out there that I've talked to a few people about. There's the passage, the uplift. What about the invention of fire by our genus, Homo? That happens 1 point some million to 2 million years ago. Before this, there is no animal on Earth that creates fire. Now, I'm going to preface this a little bit. It does only burn active carbon, so it's not CO2. We only burned trees and mostly actively circulated carbon in our Homo genus, because it goes before Homo sapiens. So it didn't pull fossil carbon, which is really different. It actually adds amount CO2 to the Earth. And so it shouldn't necessarily affect the greenhouse gas forcing. But what I'm thinking is fires, and the use of fires, are going to change the landscape color, albedo, and it's also going to produce aerosols in the air that would normally not been there in a new way. Like smoke would have been continuous rather than periodic. Now, could
I
that have
think,
affected
but
anything? Yeah. So go ahead.
my instant thought is
Yeah.
that yes, human would start fires, but like I would highly assume that like periodic fires from dry periods and lightning and all of this stuff has still occurred, right?
Yeah. Yeah.
So you still have like a lightning strike on a dry day or a dry period is still going to cause a large fire. And like current situations, right? Like in California and stuff, we have hundreds of people throwing water on it, containing it, closing it. We have roads that blocks areas of where the fire can sort of extend to. Like during that time period, it just ran until it ran out. And I would assume that you would not necessarily be able to distinguish between the amount of fire. That's just my initial thought of this.
That's
That
a
I
very
don't think
good point.
humans would actually cause that much of a spike and increase in order to change the global,
Yeah.
the global,
The global
or
surpass
the
the
atmospheric
natural
like
forcing.
composition.
Yeah. The natural
And
forcings.
yeah,
Okay, that's a great answer. And I've talked to other people and they're just like, I've never heard that. Cause I think about it like this, like fossil fuels, what we do is, we're essentially releasing energy through chemical reactions. And in terms of fossil fuels, we're pulling carbon that would have been fossil carbon and then putting it essentially back into the cycle. Hence the
yeah.
reason CO2s are
And we
going.
and we would be doing that with I guess with trees too, right? That's like if we're burning woods for fires and stuff, like that's release of CO2.
But it doesn't overall because if you cut a tree and burn
I
it,
would
yeah.
I would I would assume that like one
Yeah.
I'm just throwing out numbers here, like one forest fires a million years back would probably produce as much as
Whole
thousands of
population.
ancestors
Ancestors.
like starting small fires, or even like thousands of them starting small fire.
Yeah.
So I don't actually think that there would be. Sure,
Mhm.
we started periodically and continuously doing these fires, but I don't think there's a signal increase in it.
Mm-hmm. And you would think
But
you would have
yes,
found it maybe in like soot or black carbon, like if there's a distinct, like, because the invention of fire is like 1 to 1.5 million years ago. I mean, I think
yeah,
1 to 2, and it's really actually debated because it's hard to determine is it a natural fire or caused by humans. But I
yeah,
think like the best ones that are like it's in a circular rock, it's clearly someone built a little fire. It's like 1 to 2 million years ago, and I think it's Homo erectus.
yeah,
So fire use by animals on Earth is even younger than ice, essentially. And
yeah,
it just seems like, why does that just seems like it's like a huge accomplishment that was created by our bipedal ancestors to harness that energy. Like, but yeah, I could see exactly what you're saying. Like one major forest fire across the savannah is like the equivalent of every Homo erectus's fire that they made for
yeah,
cooking an
like yeah,
antelope for the whole year. And that totally makes sense. And yeah, how do we determine whether or not it's lightning strikes or volcanoes or all the natural things? Fire has certainly been around for millions. I mean, it's been around since the beginning of Earth. So it's a
yeah,
natural thing. Yeah.
yeah.
But yeah, I
That
think
was fun
I think
to know.
that was one thing I was throwing out. And then maybe like if you're at a party, you'd be like, yeah, this idea, like, I don't know. Like, but I think you've pretty much debunked it right there. I don't think there's
Sorry,
anywhere to go with that. Okay. That was a wonderful conversation, Marie. I really
that was
appreciated
fun.
you being on here. If you're watching this and you enjoyed the conversation, you like science communication, please subscribe to the channel. All you have to do is click subscribe. I have a lot of people returning to watch videos,
Nice.
hundreds. Maybe hopefully we'll get up to thousands, but I'm not seeing as many subscribers. And if you don't want to subscribe, all you have to do is like the video, and that really helps out the channel reach more people. because what I'm trying to do with this channel is give scientists a voice on the internet so we don't have to hear about their results through other people, other podcasts, and I've had plenty of experiences with the press releases from research, and the coverage of the research on the internet is terrible
Yes.
for your own research sometimes, and you're like, oh my gosh, I cannot believe it, or like, I didn't mean it that way. But in this way, you have this whole time to talk and get your story out the way you want it to be heard in the public.
Thank you for that. Thank you. It's been fun. It's been fun talking about this. I haven't talked about it for a couple of years now, so that's
It's surprisingly fun. It's like, I have, like, when you go to AGU or EGU, it's like you do this and you'll be at like dinner afterwards and you look down, it's been like 3 hours.
yeah.
It's like, I need to capture this
Yeah.
on a podcast channel and just get stuff out there. There's always, scientists have so many interesting stories. There's a lot of really
That is
interesting.
true. That is true.
They usually have a lot of life experiences that most people don't have. Like, you lived essentially in Antarctica.
Yeah.
So you're maybe one of the few thousand, maybe people
Pretty much,
ever
yeah.
in the world to go there. And that alone, having that story told by you, is something, firsthand account that historians of the future may want to see or hear
Yes.
about. If we maybe do melt those ice caps, they'll be like, what were the scientists seeing back then? And you'd be like, here it is. Do you have any shout outs at the end? Do you want any papers coming out or any projects that you want to shout out or thank?
No, I don't think so.
Okay.
Not on the top of my head.
All
Doing
right.
a lot of cool research as always, but yeah.
And you're still in research at Berkeley right now, and
I'm doing a lot more method development, so finding new ways of getting better results and doing better than what we're already doing in the actual measuring side of it.
there's
But
sure
yeah,
to be some exciting work coming out then.
there'll be some coming out of that. Exactly.
Amazing. All right, Marie. Well, thank you again for joining us.
Thank you so much for having me. Bye.